Hi, and welcome to Unit 1.2b, Foundations of Chemistry, Notes Video, Part 2. Again, we're focusing on the second half of key question 1, how do we represent matter? In this video, be sure to annotate. We are looking at the VSEPR models of the 6 basic representations. And just as a reminder from Part 1, remember VSEPR theory is important because the three-dimensional shapes it explains three-dimensional shapes which support bond angles and polarity. Now, in the last video, we focused on using VSEPR to explain bond angles. We're going to focus on polarity here. So, polar versus nonpolar. You probably recall that a polar molecule has a positive and negative side. And before we dive into the meat of this lesson, I just want to present to you what's called these electrostatic maps. These are computer-generated images that show where the electron density is in a molecule. And the way that they coded this electrostatic map for CH2Cl2, the region with more electron density, so that means it has a lot more electrons in that area at a given time, that region is shown in red. So this portion here has higher electron density than the blue portion. And if it has higher electron density, that means that it's partially negative, and this side is partially positive. So this is a polar molecule because it has both a negative and positive side. Here are a couple more examples of polar versus nonpolar molecules. So NH3 is a polar molecule. You can clearly see the large electron density at the top where the lone pairs are on the nitrogen, and where the hydrogens are, it's not very electronegative. Okay, so the electron density is on top of the nitrogen, and then where the hydrogens are, it's low electron density. So this side's negative, that side's positive. With formaldehyde, CH2O, it's where the electronegative oxygen is. That's where you have the electron density, and that should make sense. And where the hydrogens are, it's low electron density, so that side's positive. Now, you may be wondering something like CO2. You're looking at it and you're saying, well, oxygens are electronegative and carbon is not, so shouldn't that make it that this molecule is polar? Well, this molecule is actually nonpolar, and the reason for that is in order to be polar, you have to have a positive and negative side, meaning that if you were to split something like NH3 in half, you can split it off into the negative side going one way and the positive side going the other way. The same thing with formaldehyde. If you were to split this, you would have a negative side going one way and a positive side going the other way. For CO2, no matter how you split this, if you were to split it here, or there, you wouldn't have just a negative and a positive side separating. You would have a combination of negative and positive sides that are separating. And so that would make CO2, visually, this would explain why CO2 is nonpolar. So I'm throwing around this word electronegativity. Remember that electronegativity is the ability of an atom to pull electrons toward itself in a covalent bond. So you can sort of think of it as a tug of war. Covalent bonds, atoms in covalent bonds, they share electrons. And if you have a very electronegative atom, it wants to pull the atoms more toward it than a non-electronegative atom. In the periodic table, you notice that fluorine is the most electronegative, followed by oxygen, and nitrogen and chlorine are about the same. So you can picture this football player being fluorine, and then this little baby being something like hydrogen, where hydrogen is not very electronegative and fluorine is, so it's going to pull the electrons toward it. Since electrons are negative, if you pull electrons toward you like this football player would do, or fluorine would do, then you would have a partial negative charge. And since this baby is losing the electrons that it's sharing, it's not losing it completely, it's just that the electrons aren't very close toward it, it's going to be slightly positive. Now, this is important because atoms with significant differences in electronegativity will form polar bonds. But polar bonds in and of themselves are not enough to make a molecule polar. And this is where VSEPR comes in. So we have to use both our understanding of electronegativity, that's what this stands for, and shape to determine if a molecule is polar or nonpolar. So if we look at the example with water. Water is a polar molecule, and we can start by looking at the bonds. That's a good place. And remember, oxygen is one of the most electronegative atoms, and hydrogen is not very electronegative. So the electrons are going to go towards the oxygen in each of the hydrogen-oxygen bonds. We can draw this bond dipole as these blue arrows pointing towards the more electronegative atom. Now, VSCPR tells us that the shape of H2O is not linear. It's actually bent because you have some lone pairs, which are not shown here, but it's a bent shape. So we know from this shape, and if you understand a little bit about vector analysis, that these vectors or these dipoles will not cancel out, okay? Because they're not, they're unable to cancel out because they're not going completely opposite directions, for example. And so overall, we have what's called a dipole moment, or which represents the polarity of the molecule pointing up towards the oxygen, meaning that this is where the negative side would be, where the arrow is, the arrowhead is, and this is where the positive side would be at the bottom of the arrow for water. So negative by the oxygen and positive by the hydrogens. For a nonpolar molecule, we again will utilize shape. An easy example would be when they're the same exact atoms. Well, then those case the bonds themselves are nonpolar, and if there's only like two or whatever, if the bonds themselves are nonpolar, then we know it's a nonpolar molecule, so that's fine. But there are also cases like with CO2 where you can have polar bonds, like carbon-oxygen bond is a polar bond, but the dipoles cancel out because they go in opposite directions. We saw from the electrostatic map that CO2 was nonpolar, but now we can also see from the dipoles, since they cancel each other out, that it's nonpolar. Same thing with BF3. This is a very symmetric or even molecule. All of the bond dipoles, for the boron-fluorine bonds, are going to cancel out, and so this is nonpolar. Now, even though this is super important for understanding polarity, it's not always easy to do, to figure out something is polar or nonpolar just by looking at it. So what we're going to do is use some quick tricks for polar versus nonpolar. And the first quick trick is for diatomic, where there are two atoms, and that means exactly two atoms. We wouldn't count water, H2O, because that molecule has 3 atoms in total. So if it only has 2 atoms, we utilize the differences in electronegativity to determine if it's polar or nonpolar or even ionic. The second quick trick is if you have carbon and hydrogen atoms only in your molecule, it is always nonpolar. And the last one, if you have more than 2 atoms and it has atoms other than just carbon and hydrogen, then you're going to use this quick nonpolar checklist, which is it's nonpolar if all the terminal atoms are the same and no lone pairs in the central atom. So if you can check both of those off, you know it's nonpolar. All right, let's try to start understanding using these quick tricks for HCN or hydrogen cyanide. After you determine whether or not this is polar or nonpolar, we're going to come back together and I'll reveal the answer. Okay, so this is a polar molecule. First off, it has more than 2 atoms in it, and it's not just carbon and hydrogen, so we're looking at this checklist at the bottom. And the checklist says, first thing, are the terminal atoms the same? The terminal atoms are the ones at the end, hydrogen and nitrogen. They are not the same, so automatically I know it's nonpolar because I can't check that box off. Okay, so we talked about the quick tips. They are or quick tricks, they are so useful for quickly determining whether or not something is polar or nonpolar, but they will not help you explain, particularly on something like an AP exam. You have to explain polarity based on science and scientific reasoning. So remember, polar structures are asymmetric. We saw that in some previous slides. Oops, sorry about that. They're asymmetric. That means that the dipoles do not cancel out. And there's no net dipole or dipole moment because the dipoles do not cancel out. Nonpolar, you want to use language like the structure is symmetric or the dipoles cancel out. or they have nonpolar, is constructed of nonpolar bonds. All of that will help to explain why something is polar versus nonpolar. So over here on the side here, I just have an example of what that could sound like. It doesn't have to sound like this, but it could sound like that in explaining polarity. The main thing being, use the quick tricks just to quickly determine if something is polar or nonpolar, but you have to utilize this language here when explaining. I hope you found this video helpful. Have a quality day.